Okay, so what we showed in last time in class was that if we have a relation R on a set S, then we get, when we look at the set of all classes of the elements of S with respect to R, we get a partition exactly when that relation is an equivalence relation. And it turns out, moreover, if you have an equivalence relation, then you look at the classes, you get a partition. So the concept of a partition and equivalence relation is encoding the same information about the set S and the way the elements are divided up amongst S. So what we did was then we looked at this example of the relation that says that two integers are related when their difference is a multiple of n for some fixed n. This n is the same as that n, which is the same thing as saying n divides their difference. And what we noticed was this was also the same thing as the set of all xy's, such that x is congruent, or y is congruent to x mod n. So this is just nothing more than the equivalence than the relation that we started talking about in the very beginning. We showed that it was an equivalence relation, and the set of all integers, when we look modulo this relation Rn, is nothing other than z mod nz, as we said before. So this is just the class of 0 mod n, the class of 1 mod n, the class of 2 mod n, all the way up to n minus 1 mod n. And we just remember that these are the multiples of n. These are the things with remainder 1 when divided by n, and then 2, and then n minus 1. Okay. So when we look at this, the integers modulo the relation Rn, we get nothing other than z mod nz, and that's because these two things are the same. And so what are these two things? These are simply the set of all, so x mod n, which is the same thing as x mod r sub n. These again are just x comma y, such that n divides x minus y, or y minus x. Since it's symmetric, it doesn't matter which way we write it, which is the same thing as saying that we're looking at x mod y's, such that if their difference is divisible by n, that means that I can write them as x congruent to y mod n. And so we just remember what these different notations mean. So what would it mean that we have A is, the class of A is equal to the class of B, so the class of A mod n is equal to the class of B mod n, is true exactly when they are not different. So that means that A is in the class of B mod n. That tells me that n divides A minus B, or maybe taking one step back, that means that B comma A is in my relation, and that tells me that n divides B minus A. All right, and so that tells me that B minus A is equal to nk for some k in z. And that tells me that if I can write A. So I can write that B is equal to A plus nk, right? And that tells me that, actually I want to write it the other way, I think. Yes, so let's do it the other way. So let's write it as A is equal to, so minus A is equal to minus B plus nk. That tells me that A is equal to B minus, or let's write it as plus n times minus k. And that tells me that A is congruent to B. Let me write it on the next line. That tells me that A is congruent to B mod n. That's the definition of what it means, right? Okay. So that we showed that if the class of A is equal to the class of B, then A is congruent to B mod n. Suppose we want, this is an if and only if, so if we want to go the other way, then we would start with this statement here. A is congruent to B mod n. We'd start here, A is congruent to B mod n. And then what we can do is we can just trace these arrows back, because each one of these arrows was an if and only if. So in fact, saying that two classes are equal, it means nothing more than that the one is congruent to the other mod n, or that n divides A minus B. Okay, so we've got lots of different ways of saying that, that the class of A mod n is equal to the class of B mod n. We just proved that this is equivalent to saying that A is congruent to B mod n. And we know that that is equivalent to saying A minus B is equal to a multiple of n. And we know that that means that n divides A minus B, which of course is the same as saying that n divides B minus A. And we could also say that A and B have the same remainder modulo n. Okay, so I'm going to pause the video and I'd like you to do example 3.7.